So we're going to look at an example that involves higher order variation of parameters here. So let's say we are given the equation y triple prime plus y prime is equal to secant of t. So to begin, we would find our homogeneous solution. So we would say, using the characteristic polynomials here, so r cubed plus r is equal to 0. This gives me r times r squared plus 1 is equal to 0, which results in us concluding r is either 0 or positive or negative I. So the 0 corresponds to the solution of a constant, the positive and negative I, the cosine t, and the sine t. So there is our homogeneous solution. Now, it's our goal to also find a particular solution, such that when I take two derivatives, or one derivative, and add the triple derivative to it, I end up with secant of t. And that's not very clear to me at all what that would look like. So that's why I'm going to use the method of variations of parameter. And so what's interesting about variations of parameter, right, our guess in general is just the same as the homogeneous, but we replace the constant coefficients with functions here that are functions of t. That right there should have been a 3. Oh my goodness. So this should be NV3 sine of t. Now, what will happen generally if I were to actually plug these in, take derivatives, it will reduce to a simpler system of equations, and that equation would have all these v's will have primes, so v1 prime, v2 prime, v3 prime. And the first equation would be just that, these v1 primes equaling 0. In the next equation, we would have to take a derivative of the coefficients of the v1. So this would be like the y1, y2, y3 in the notation of the book. So the derivatives of those. First derivative would still be equal to 0. And then when we do the second derivative, it would be equal to our forcing function secant of t. Notice we would have 3 equations because we have 3 different unknown variables, v1, v2, and v3. And so instead of writing it as a complicated system, though, I'm going to write it in our matrix form. So the matrix form would look a little bit like this. So this will be my matrix of coefficients. On the outside, I know in that system, just from the method we've seen, the v1, v2, v3 will end up with a prime there, so it will be a derivative. This will be equal to 0, 0 secant of t. So we just force everything to be 0 except the very last one, secant of t, which is something that we're allowed to acquire. And then the coefficients are here, those y1, y2, y3. So in the notation of the book, 2y3, y1 prime, y1 double prime, etc. And so let's put in our values there. And so y1 corresponds to just the number 1, cosine of t, and sine t. Taking derivatives going down, we get 2 zeros. We get a negative sine t and a negative cosine t. And then we get a cosine t and a negative sine t. So this is our system of equations that we need to solve. And so at this point, we can just go ahead and move into Cramer's rule, which is how I'm going to do this one. It'll be much more straightforward than trying to solve that system in any other way. So for Cramer's rule, I will need the Wronskian of this matrix A, right? So if we call that matrix A, recall Cramer's rule says, well, the value for your first element x would be, the matrix determinant of AX over the determinant of A. And what do those mean? Well, determinant of A is this determinant that we have here, which is equivalent to the Wronskian of the y1, y2, y3. And so let's start with that. So the determinant of A, which is really the same thing as the Wronskian, is equal to here. I'm going to do it in a different color. Well, let's just do it. So it'll be 1 expanded upon the first column times, that'd be sine squared t minus negative, so plus cosine squared t, So the Wronskian is just 1. So that tells me my x, so the first, right, v1 prime is really just the determinant of A, where I replace the first column with this vector. So let's do that. So if I were to actually put it into notation here, what would that look like? So if I call it, maybe I'll call it AX still. I think that's fine for teaching purposes. X just being the first component. So X is really V1 prime. So the determinant of AX is really the determinant of this. So 0, 0, secant t, cosine t, negative sine t, negative cosine t, negative sine t, cosine t, sine t. What's great about this is that we have the first column, which is mostly zeros. This will make it pretty straightforward to calculate. So to find this determinant, it will end up being secant of t times the determinant of this sort of upper right corner, which would be cosine squared minus negative, so plus sine squared t. But that's just secant of t. Great, so there's your v1 prime, so we have that. And then we continue along in a very similar way. For v2 prime, since we're divided by the Wronskian, which is 1, it also just turns out to be this. So the first column stays there. Oops, let me spread that out. 1, 0, 0. The second column is now your 0, 0 secant of t. And then your third column stays as the original. So this then gives us a nice solution for expanding upon, pick a row or column. So if I do, let's say I just do the first one. So 1 times 0 minus, so negative secant t cosine of t. But wait a second, secant times cosine is just 1, so that's negative 1 is your v2 prime. And then in a similar modus operandi, pulling up my Latin there, we have 1, 0, 0, cosine t, negative sine t, negative cosine t, and then sticking in 0, 0, secant of t. So pick your poison here. I'm going to expand upon, let's just do the first column again. So it'd be 1 times negative sine t secant t. So that's your v3 prime. Great, so now our job is to integrate these. And so let's just go ahead and maybe I'll just move them down here to remind us what they are. So v1 will be the integral of secant of t dt. Right? v2, let me grab that, was negative 1. v2 is the integral of negative 1 dt, and v3 is the integral of negative sine t secant t dt. Alright, so now we could take these ones one at a time. So for the first v1, there's 2 ways of going about this one. So if you have it, this is one that's often on a table. So if you want to look that up, it would just end up being the natural log of secant t plus tangent t. There is a way of getting it though if you're curious. The trick would be to, rather cleverly I suppose, multiply the top and bottom by secant t plus tangent t, secant t plus tangent t dt, because then you could use u substitution, where the derivative of secant t is secant squared. So notice this would simplify to secant squared t plus secant tangent. So if my u was secant plus tangent, this would be du would be secant squared plus secant tangent all times dt. And so you can do use substitution, and this turns into a natural log with that substitution, and so you end up with the natural log which is down below. So that's how you might get there. I don't know what's easier to remember the solution, or remember that there's an interesting thing to multiply by. So there's your, let's put it over here together, that's your V1. Likewise, and maybe I'll do it, since it's kind of skinny here, I'll do it in a different color. So for V2, the integral of a -1, I'm just going to call it a negative t. And notice I am here not putting in an arbitrary constant, since I'm looking for a particular solution. Any particular solution, right? So I don't care if it's +1, +2, +3. I'm just going to add 0 because that makes it much more easy for me. And then the last one here, notice I like to rearrange these things in terms of sort of sines and cosines. And that helps me think, oh yeah, if I do a little u sub here, then suddenly, if u is cosine t, then du is negative sine t dt. This just becomes 1 over u du, so this is just the natural log of cosine. So that's my V3. So putting it all together then, my particular guess, right, my y particular, was, so this natural log secant t plus tangent t, that's my V1. Let me zoom out for a second. Remember, V1, my particular guess, shows it way back up here. V1 is just by itself, so that's just hanging out. V2 will be multiplied by a cosine, and V3 by a sine. So there's V1. V2 was negative t, but we're multiplying it by a cosine, so it'll be minus t cosine of t. And then V3 is plus the natural log of cosine t times sine t. So here's a particular solution to this problem. And I never would have guessed that is what it was from inspection, but we can get it with only a moderate amount of pain from our method. And if you want to put everything together, you definitely can do that. You're homogeneous with C1 plus C2 plus C3. I might as well do that just to be perfectly consistent. So there's your particular. I'm just going to add it there since this is recording. It's live. So the whole solution, if I wanted to include that here as well, would have been y is equal to C1 plus C2 cosine t plus C3 sine t plus that. So that big long equation is the general solution to this equation at the top, right? It looks so unassuming, so nice. But now we see that it has a rather gross general solution. Now notice the general solution is every possible solution. So you could likely find simpler solutions. But every possible solution could be written, let me zoom out even more, in this form. All right, great.